All right, so this is part 2 of the derivative of a function lesson. So we're going to say that a function f is differentiable at a if f prime of a exists at that point. It is differentiable on an open interval, a to b, or a to infinity, or negative infinity to b, or negative infinity to infinity, if it is differentiable at every number in that interval. Example 1. Where is the function f of x is equal to the absolute value of x differentiable? So the first thing let's recognize is that differentiability, or the derivative, is just the slope along the curve at any particular point. So with our function here, our absolute value of x, we know it looks kind of like this. It goes through the origin, 0, 0, and we have this V shape. Now, if I look at any point along this left-hand side of the y-axis, I can see that the slope is -1. Because mathematically speaking, the curve over here is represented by the line -x, and the curve on the right-hand side is represented by x. So we know then that the slope of the curve on the left is a -1, and the slope of the curve on the right is a +1. So we have here our slope being -1, and here our slope being +1. Meaning, if I were to actually find the derivative on the left, right, I would get f prime of x is equal to -1. But that is only when x is less than 0. Versus on the right, if I found the derivative, f prime of x, it would be 1. But that is only when x is greater than 0. Now the problem lies where we're at 0, because at that point, the slope is different on the left and the right. Because of that, we're going to say that it is not differentiable at that point. So where is the function f of x equals absolute value of x differentiable? Well, it's differentiable on the intervals -infinity to 0, union 0 to infinity. So everywhere but that point where the two sides of the absolute value meet at the origin. All right, let's introduce a theorem. If f is differentiable at a, then f is continuous at a. Remember, continuity suggests that the function's curve has no jumps, no holes, no gaps. Note the converse's theorem is not true. So continuity does not imply differentiability. So as in the example on the previous page, this function was continuous. There was no hole at 0, but it was not differentiable. Okay? But if it is differentiable, then it must be continuous. All right, there are 3 ways in which a function is not differentiable at a point. So if you look in the first image here, it's very similar to what we talked about on the absolute value of x example. You'll have here a sharp corner. And this corner here creates a point of not being differentiable. Because what happens is on the left-hand side, you see we have this increasing slope. And then on the right-hand side, we have this decreasing slope. And so at this point, the question is, which slope is it? And it's actually neither. So it is not differentiable at point A. Another example of where it can't be differentiable is when we have a discontinuity. So we see here in this graph of g of x, we have what's called a jump discontinuity. And so that at this point, it's impossible to determine what the slope is at this point. Because on the left, it's one value, and then on the right, it's another. Similarly, a function is not differentiable, here function h, if we have a vertical tangent at a. So you see this here, the tangent line is actually vertical. We know that vertical suggests undefined. So at that point, it would not be differentiable. That would be a divide by 0 error. All right, we're going to introduce for the first time higher order derivatives. We're going to say this. If f is a differentiable function, then its derivative, f prime, is also a function. Therefore, we can consider the derivative of f prime and denote it by f prime prime, or f double prime. This new function, f double prime, is called the second derivative of f because it is the derivative of f. Using what's called Leibniz notation, we can write the second derivative of y equals f of x as d dx dy dx is equal to d2y dx squared. Okay, and this is our notation in Leibniz notation for our second derivative, whereas this is the first derivative. Note these are just different representations of this same prime notation. All right, given the function here, f of x is equal to x cubed minus x. Find f double prime of x. Okay, now in order to do this, we need to first find f prime of x. So we know that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Plugging that into our function, we get the limit as h approaches 0 of x plus h cubed minus x plus h minus x cubed minus x all over h. After expanding, this becomes the limit as h approaches 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus x minus h minus x cubed plus x all over h. We will note that x cubed cancel and that the x's cancel, leaving us with the limit as h approaches 0 of 3x squared h plus 3xh squared plus h cubed minus h over h. Factoring out the common h from each term and canceling the denominator gives us 3x squared plus 3xh plus h squared minus 1. Direct substituting 0 for h gives us 3x squared minus 1, because all of the terms that have h will cancel. Now that is our first derivative. To find our second derivative, we will do the exact same process, but now we're taking the derivative of the derivative function. So this will be our starting function. So we have the limit as h approaches 0 of f prime of x plus h minus f prime of x over h, which in this case becomes the limit as h approaches 0 of 3 times x plus h squared minus 1 minus 3 x squared minus 1 over h, which then becomes the limit as h approaches 0 of 3x squared plus 6xh plus h squared minus 1 minus 3x squared plus 1 over h. We will notice here that 3x squared cancels and that negative 1 and plus 1 cancel, leaving us with the limit as h approaches 0 of, I'm going to go ahead and factor out the h, so 6x plus h. Direct substitution of 0, 6x plus 0, so our second derivative is 6x. All right. Now, it says sketch a graph of these on the same coordinate plane. So let's see if we can make a small sketch here. So there's our coordinate plane, and we want to graph f, and it says f double prime. Let's actually graph all three. So we have here 6x. Let's just approximate that. So it's a linear equation with a relatively steep slope. Then we have our 3x squared minus 1. So that will start at, let's say this is negative 1. 3x squared is relatively steep. So something like that. And we're going to pretend these are more accurate than they actually are. And then we have our x cubed minus x, which we know crosses at negative or positive 1 and at 0 and at negative 1. And I think we played with this one the other day. So it's going to go down, up through 0, and then back down. And we'll play with a better sketch of that later on. If you would like, I would say graph that on your graphing calculator or Desmos to get a more accurate sketch. All right, this is our last example. So given the same function, f of x equals x cubed minus x, given the first derivative and the second, find the third and the fourth. Okay. So let's start with the third. So the limit as h approaches 0. We want to find the third, so we're going to use the second of x plus f double prime of x plus h minus f double prime of x over h. And this is going to give us our third derivative. And that is the limit as h approaches 0. And our f double prime of x is here, so 6x. So 6 times x plus h minus 6x over h, which is the limit as h approaches 0 of 6x plus 6h minus 6x over h. 6x's will cancel, the h's will cancel, so we're left with the limit as h approaches 0 of just 6, which is 6. So our third derivative is 6. Now, last but not least, let's find the fourth derivative. So that is the limit as h approaches 0 of f triple prime of x plus h minus f triple prime of x over h, which in this case is the limit as h approaches 0 of 6 minus 6, because in all situations, triple prime gives 6 regardless of the input for h or for x. So this becomes the limit as h approaches 0 over h, which is the limit as h approaches 0 of 0, which is 0. So our fourth derivative is 0. All right, now get some practice.